so ready to go. Find the slope and y-intercept of that linear equation. Ready, set, go. And make sure that we're all on the same page. So with this, remember that the slope-intercept form is y equals mx plus b. A defining characteristic of this is that the y is on the left side of the equation, and it is all by itself, and all the other stuff, whether it's numbers or x's or whatever it is on the other side. So my first move is I want to get this stuff away from the y term, because the y has to be by itself. So the way that I'd get that 18 over to the other side would be subtraction. The way that I'd get the negative 7x over to the other side would be addition. So my first step would be, I'd probably just do those two things in one step. I'd say plus 7x to both sides, and I'd subtract 18 from both sides. Does that make sense? You could do it in two steps, or you could just do it in one. I'm going to do it in one step. So on the left side, these two would add out, these two would add out, leaving me with just 3y. So that's good. 0 plus 7x minus 18 is just 7x minus 18. Now, when you compare this with this, remember our goal is to get the y all by itself? And right now, you can clearly see I've made a lot of progress, right? There's a lot less stuff with the y, but there's still a 3. How do I get rid of the 3 on this one?
Divide it.
Divide, because it's 3 times y. So I'm going to divide everything through by 3. So I usually write it like this. Like so. The 3's cancel. This leaves me with y. That was my goal, to get the y all by itself. So I've done that on the right side. You could write it as 7x over 3, but 7x over 3 is the exact same thing as 7/3 x. Same thing. 18 over 3 is 6, so it's minus 6. Then what I would do is I would just compare my slope-intercept form with this. I'd realize that m is 7/3, so I'd say the slope is 7/3, and I'd say the b is negative 6, so the y-intercept. I would take this if you just said the y-intercept is negative 6, or if you said 0 comma negative 6, same thing. I think I'd go either way with that. They're both pretty clear descriptions. Okay, any follow-ups there? Okay, awesome. So then let's go ahead and move on to the next one. I am going to change this. Hey, please listen. I am going to change this. Sorry. Gears fairly fast. Let me just point out the most common error, and hopefully this will be a help to you. Slope formula, change in y over change in x, like so. I'd like to show you the most common error, so maybe you'll be on the lookout for it, right? If it's the most common error, you'd want to make sure that you know about it. Okay, so y2 would be negative 2 minus y1 is 6. Let's hold the markers, please. Thank you. X2 is 4. And here's where we had the biggest issues. 4 minus 1. So I just want to point out why that's not right. This minus sign is right here. I've just transferred that over because that's part of the formula. And when you look at it that way, can you see how I've made a mistake there? I've used 1 for x1 instead of negative 1, right? So we tend to write just like a minus sign and think, well, that's the minus sign, but it's really not. It really should be 4 minus, and the x1 was negative 1. Of course, that changes things. This ends up being negative 8, but it's 4 plus 1 in the denominator, which is 5, instead of 4 minus 1, which is 3. So this would be your right answer right here, negative 8/5. And like I said, we're pretty much all the way there. Any questions? All right, cool. Well, then let's move on to some new stuff. I'm super curious to see what you do with all of this. So let me scroll to where I want to scroll. Yes, right here. Number 9. Solve the system of equations. So it's from late in the first semester. It's from like last November. Notice I didn't specify method. You could use multiple methods here. I think one method is probably better than the other. So solving a system, you need to have at least 2 equations to have a system of equations. We got 2 of them up there, right? So if we were graphing these, we'd be looking for the intersection point. Maybe you remember that? But I don't think that that's the most efficient way with this one because, listen really carefully, this is a key thing for you to get. Or just remember, because you had this at one point. The key thing is, did you notice how the first equation is already solved for y? When you see something like that, that should tell you that this is going to be best solved using substitution. Did I spell that right? Substitution, I think I did. Substitution would be the best method. And all substitution really is it's what you think it is. It's when you remove one thing and replace it with something equivalent to it. The analogy I used in class was, if I'm at a restaurant and I don't feel like having the little bowl of coleslaw, I'd rather have some vegetables. I say, you know what, could I substitute some vegetables in for the coleslaw? I'm not a fan of coleslaw. It wouldn't make any sense for me to say, you know what, I don't want the bowl of coleslaw, will you give me 17 large pizzas? That's not an equivalent trade, is it? But some vegetables for some coleslaw maybe is equivalent. So because, this is so huge, because, listen, stop moving around. Just watch, listen. Seriously. Because this is on the left side of the equal sign, and this is on the right side of the equal sign, that means that no matter how different they look, they have the same value. No matter how different they look, they have the same value. Therefore, in the other equation, I could replace one with the other. And that's the principle at play here. So what I can do then is wherever I see a y in the other equation, I can remove it and replace it with what it's equivalent to. That's what I'm going to do with substitution. So it's going to be x minus 2. The y used to be right there. And what I can do is I can get the y out of there, because the y makes me have two variables instead of one. I can replace that y with what it's equivalent to, and that would be 2x minus 1. You see how I've made it like a nice, neat little swap there? The y is gone, the 2x minus 1 is in. You see it? It's the exact same equation, just I've replaced the y with what it's equivalent to. So really often with the distributor, with the substitution, the distributor property comes into play. Maybe you already saw that. This negative 2 gets distributed. So this would be x minus 4x plus 2 equals negative 4. I'd combine my like terms right here and get this. And then it's just an issue of solving the linear equation, which I think we're pretty decent at. So I'd subtract 2 to start off with. And so I get negative 3x equals negative 6. Dividing by negative 3, I end up with x is equal to positive 2. So if you remember solving a system like this, we're finding the point of intersection essentially. And so what we need to do is find the y to go with the x. How do I find the y to go with the x? Plug it back in, yes. And of the two equations, I'd say the top one is the better one to plug back into because it's already solved for y. So I would write y equals 2. And I know that x is 2 now. So I replace the x with 2. Y equals 2 times 2 minus 1. That's just 4 minus 1, which is 3. So we'll often write our answer as an ordered pair 2, 3, because it really is an intersection point on the graph. Okay. Couple of common errors. One of them is just totally careless. A lot of the questions I walked around, the negative on the 4 just poof, gone for no good reason. Be super careful that they're not doing that. And then there was some confusion about what is substitution, how do I solve this? Some folks kind of went really the long way around but did well. Others maybe got themselves a little confused. So just an encouragement to you to do something like that. Remember this? I got another one, another system. So let's try that. This one's different. Number 10. Let me discuss with you guys real quick. Sorry, last once. So it's interesting going around seeing the various methods that you all used. Can I show you like what clues me in on what to do? I look at these two equations and I see this right here. This is a big hint to me that the y's, as it currently is written, the y's are opposites, right? One of them is positive 1 for a coefficient, the other one has negative 1 for a coefficient. That tells me that the better method, or the best method here, in my opinion, would be elimination. And elimination is often referred to as addition, because all you're really doing is you're adding the equations vertically, you're adding the like terms essentially. So what I'll usually do is just draw this little line underneath. You could even put a plus sign right there if you wanted to remind yourself that you're really adding. And I'm just going to add the like terms. So 2x plus 3x is 5x. Negative y plus positive y adds out to be 0, so I'm not going to write anything there. 2 plus 8 is 10. So what I've accomplished by doing this is the same thing that I accomplished by doing substitution. I've taken an equation that has 2 variables and turned it into an equation that has 1 variable. Yes, ma'am. Oh my goodness. Maybe if I looked up there I would know this. Magic, here we go. There it is. Thank you for pointing that out. At this point I would divide by 5. Therefore x is equal to 2. Plugging back in, we got 2 comma 4, I think, for an answer. Elimination, the better method. Okay, cool. All right. I'm making a video of this, so if you want to go back later and watch, you can. Go ahead, Haley.
Do you always add when you do elimination?
Hey, listen, it's a great question. She said, do you always add when you do elimination? The answer is, me personally, yes. Does it have to be that way? No. But well, so the point is that when you do whatever you do, whether it's subtraction or addition, one of the variables has to be eliminated. So let's say, for example, so on this one, somebody was like, you know what, I'm going to use subtraction. All right, that's fine. So if I was going to use subtraction, I'd put a minus sign down here. So 3x minus 2x is 1x. And you might look at that and be like, hey, I'm encouraged. That's pretty cool. It's gone down to just a 1x instead of something else x. But then negative y minus positive y, nothing eliminates. 2 minus 8 is equal to negative 6. So by subtracting here, I haven't really accomplished anything. But if I add, like you saw before, one of the variables gets eliminated. So if I do this, 3x plus 2x is 5x. I don't know what to do with that necessarily. Bless you. But negative y plus positive y is 0. And 2 plus 8 is 10. Well, my y's, because they were opposite and I added, got eliminated. And that's the point. You want to make sure something gets eliminated. So a different example, let's say, and I don't necessarily advocate this. I'm a fan of doing the same thing every time. So let's say you had a whole other equation. Let's say it was like, I can do a little better than that. There we go. Let's say it was like 8x minus 17y equals 12 and 8x plus 13y equals negative 27. Somebody could look at this and say, you know what? I think I would like to subtract, which is really no different than distributing a minus sign, which is what I would do. I would distribute a minus sign and then add. But if somebody wanted to look at this and say, you know what? I want to subtract this one. You could say, 8x minus 8x eliminates. This would be a time where subtraction would have been a better fit. And then you go negative 17y minus 13y is negative 30y equals so on and so forth. You need to be on your way. So try to take all the tools in your toolbox and apply them to the question. I tend to add every time just because I want to be consistent, but you could go either way. Okay, I've got another one here for you. Again, really curious to see how you do this, how well you do with this one. Number 11, factor. 5x squared minus 23x minus 10. Ready to go. And I think we're, Emily, that looks good. I think we're pretty close. I think we're missing some little details, and I think sometimes the little details really confuse us. And so I want to try to be as clear as possible with the little details. And I would say that with this process was chosen because there's nothing like magical about it. Everything, there's like a reason for everything being there or not being there or whatever. So here we go. It is factoring. It's not an equation, so we can't solve. So in the end, with something like this, if I were to take something like this and in the end say x equals this and x equals that, it's categorically not correct because this is not an equation that can be solved. And so there is no x equals. It's simply going to be breaking this down. So I want to point this out. I think fundamentally, conceptually, this is pretty important. This right here is not a multiplication problem, right? It's not a multiplication expression. What is it? Like, how are the different terms, like what's going on between the various pieces of this? It's a trinomial, and so each of the terms are being either added or subtracted, right? So that makes this not a multiplication problem. Guys, hey, this is the conceptual stuff. This is where you either get confused or don't get confused. I want to make sure that you don't get confused. So that is not a multiplication problem. Factoring is taking something like that and turning it into a multiplication problem. And we do this all the time. Haven't we done prime factors to death lately? Right? Prime factorization? Remember with the radicals?
Yeah, no, I know.
Okay, my phrase of to death was bothering you?
No,
Okay. Okay. So like, let's just say, think about it like this. Didn't we do stuff like this? Didn't we have like 19x to the fifth? Or not, 19 is a terrible example. How about 18x to the fifth? Didn't we break that down into factors by writing it as 2 times 3 times 3 and then a bunch of x's? So we've done a bunch of prime factoring lately. That's not going to work here because this is a trinomial, right? This is a trinomial, not some monomial expression. So we're going to have to use a different strategy. The strategy that we use for one of these trinomials is that split the b magic x thing. And most of you guys had this down pretty good. What we put in the x, we put AC in the top, and we put b in the bottom. And this is where it takes a little bit of work with the calculator, a little bit of thinking about multiplication and addition. And you ask yourself, what two numbers multiply to be negative 50 and at the same time add to be negative 23? And just about everybody at some point or another came up with negative 25 and positive 2. Please be ultra careful with the positives and negatives on those two numbers. So often we're just a little careless, right? And we switch those around. So be super careful with those. Once you've done that, all we're going to do now is we're going to take the b, and we're going to split it up according to what we just found with our magic x. So it's going to be 5x squared minus 25x plus 2x minus 10. Now here's the crucial step. I think this is really important. Once you have split up the b, we're going to group the first two terms and group the second two terms and add the groupings. That's the part we sometimes will forget. So I'm going to put this here, and I always add the two groupings together because that's what this is. If I don't put that plus sign in there, I've turned it into something that it's not. Okay. Once I've done that, I'm going to look for common factors. Ma'am, go ahead.
Okay, if you're saying that you couldn't just make the addition sign disappear, then why can't you just make it like appear? Like, kind of just put it there.
So it's because what it is. So addition, do you remember the properties of like the commutative property and so on and so forth?
Yeah.
The associative property is what we're using here. What we're basically saying is that with addition, what I can do is I can group a couple of terms or multiple terms together, and I can add the groupings together. But what I can't do, check this out. If I just did this, let's think about what this language means. If I've got two parentheses butted up against each other like that, what does that mean? Multiplication. That's not what this is. Think about it like this. You said, how can the plus sign just appear? I can actually do this a lot with plus signs. What if I said, and this is a totally separate example, so let's just take a little detour for a second. What if I said, hey, let's do 5 plus 7? And I said, no, wait, I'm going to change the question. I don't want you to do 5 plus 7. I want you to do 5 plus positive 7. No, I'm so sorry. No, don't do it that way. I want you to go 5 plus positive 7. Have I changed anything? No, it's still the same question, right? So inserting a plus sign between two terms doesn't really change anything. Inserting a minus sign does.
Yeah, but like if you take one of those away.
Haven't I proven it? I didn't say, no, okay, if I take one away. Has that changed anything?
No. So that's why I'm saying.
Have I changed? No, listen, let's go with your thought. Let me finish your thought.
Okay.
I just took the second one away. Have I changed anything?
Nope.
Keep watching. Have I changed anything? Now it's multiplication.
Okay, but like, okay, never mind.
You know, your original question was, how is it that we can just put a plus sign in there? I think I just proved that to you, did I not?
Yeah, I was just saying like, okay,
I answered your question.
yes.
So you can do that. Okay, so the plus sign goes there. Now what I'm going to do is I'm going to factor out the GCF. So in the first grouping, 5x is what's in common. The leftovers is x minus 5. And in the second grouping, there's not an x in common, but there is a 2 in common. So the 2 would go here. The leftovers would be, look at that, the leftovers match. And we really wanted that to happen. Once you get to the place where the leftovers match, it's really tempting. And Jake, Alec, you guys were in this group. You got to this stage right here, and you said, done, factored it, over and out. Why is that not correct? Still an addition problem, but I'm one step away, right? So what I want to do here is I want to look and recognize that this and this are both common factors of the two terms, so I can factor those out. When I factor those out, the x minus 5 comes out. The leftovers would be 5x and plus 2. Now I have factored, I've undistributed, I've reversed FOIL completely. Those are the factors. What if, we talked about this a ton when we did chapter 6, what if I did all this and I felt okay about it, but I wanted to check? What could I do to check?
Foil.
I could refoil it. And if I refoil it and I get what I started with, and it checks out pretty well, I'm good. It must be correct. Make sense? You see how this is different than a little bit different than what we've been doing? What if I did this? What if I put an equals 0, and an equals 0, and an equals 0, and an equals 0? How might the...
Done magic at.
Hold on. How might... No, you're not listening. How might the instructions change?
Well, like for the when you get it factored, you have to set both of them equal to 0.
Right. I totally agree with you. And so then, what would my directions be? Like if I had all this stuff...
Solve.
Yes, instead of factor, it would be solve this thing, and then you do exactly what you just said. Exactly right. That make sense? These are deeper conceptual things, right? Things where you're reading instructions and saying, oh, the instructions say this, so I will do this, versus I see some numbers and letters, and I'm just going to do something, right? Okay, cool. We got time for one or two more here, probably just one more. That's pretty recent. I want to go back and do an old one. That's pretty recent. That's very recent. We just did those. Where's the one I want to do? You know how to do that one. This is the one I want to do. This is chapter 5.
Oh, this is so easy.
I'm glad you feel that way.
I actually don't know what I'm supposed to do.
This one, hearing your reactions like, this might be one that you need to spend some time with. I'm going to try to give you some really clear instruction. Whenever I see something like this, I'm going to think about parentheses first. So I'm going to focus on this over here before I think about anything else. I'll just leave everything else essentially alone. Here's the question. Whenever you have a base with an exponent, and then that whole thing has another exponent on that, so like it's a power to a power, what do you do with your exponents? You multiply. So for a first step, here's what I'm going to do. I'm going to leave this x alone. I can leave that y alone. Those are those two right there. They're in the numerator of the fraction. And then I'm going to multiply my exponents, so it's going to be 2 times 5 is 10. 3 times 5 is 15. The denominator stays the same. Yeah? Now, what are the exponents on the x and the y that don't have exponents? They're both 1s. Yep, so it's x to the 1, y to the 1. So whenever you have something like this where you have a base times a base, notice how that's not a base to a power, right? It's a base times a base. What do you do with those exponents? That's when you add. That's right. So 1 plus 10 is 11. 1 plus 15 is 16. And then lastly, whenever you are dividing like bases, what do you do with your exponents? Subtract. So 11 minus 7 is 4. 16 minus 6 is 10. So x to the 4th, I think I saw a few of those, right? X to the 4th, y to the 10th. X to the 4th, y to the 10th. Fantastic. Guys, I will be posting this video in a couple minutes. Practice or don't to your own peril. I hope you will. Have a great day.